Hello, my name is Ann Lee. I'm here to present the poster. This is a joint work with my colleague at UC Irvine, Blarim, CC, Professor Athena Markopoulou, and then some colleagues at EPFL, Lorenzo Keller and Cristina Fraguli, and then Julia at MIT. So the problem we're looking at is we have a group of phones of users that are close to each other, and they are say they are traveling and on a train or at a camping site, and they want to watch a live soccer match or some video stream over the internet. So each of them have a smartphone, would have 3G or 4G connections. So the default operation today is that each of the guys will take out the phone and check if he has a very good connections, and then all the guys will watch on that phone. But we realized that 3Gs work orthogonally, so basically if one guy has 500 kilobit per second bandwidth, another guy has 500 kilobit per second, they should be able to watch the stream with high quality at 1 megabit per second. So this is a scenario here. So we have a group of phones that can access the internet through 3G or 4G, and then we have like some streaming server on the internet. So the key thing is that they have to be within proximity of each other and interested in viewing some video at the same time. So this framework allow these phones to collaborate to download the video. So the key technologies we use in this framework is network coding over wireless. So the idea is that when a guy wants to send some packet to another phone, he code the packet, and then he sent to the other phone coded packet, and the other phone will decode. But we realize that this is a all-to-all scenario in the sense that if this guy downloads some part of the movie, of the video, the other guys, all other guys in the local proximity will be interested in those segments as well. So these guys will overhear what this guy sent, and so we have a local broadcast. So in our framework, we enable local broadcast for Android devices. So this is the overall architecture of our framework. So we have a user interface, we have storage. The three main things are the micro download, which schedule which part of the video segment each of the phone download. The micro NCP2, which is the local P2P communications protocol I will describe later. And then the micro broadcast, which allow you to broadcast in Wi-Fi in very high speed for Android devices. So this is some snapshot of the user interface. So we have, so this is the main GUIs where you can monitor all the information of the streams. And then you can also, this is the configurations where you can select which protocol you want to use. And then and these are like the download in, this is an in-action download, so you can see what segments are missing and what segments are downloaded and so on, and all the statistics. So here I just explain these three main components in more detail. So micro download coordinate segments to download to all devices, and it handles errors, and the download of each, the rate at which each of the phone downloads should be proportional to its 3G rate. For the micro NCP2, this is local P2P communication protocol. So you can think of it as BitTorrent, but it exploits network coding and overhearing. So here, micro broadcast is basically you can think of it as a link layer in the applications that allow you to broadcast in high speed. So we utilize unicast and overhearings. So the problem with broadcast is that you cannot adjust the rate if you use just IP broadcast. So we have to go with this route. And so we implement it on Google Nexus phone. So this is the Google reference development phones. It has 1 gigahertz CPU, 500 RAM, and it has all the connection we need. So it has 3Gs, it has Wi-Fi, and then some Bluetooth. And then the software is on Android 2.3, which is Gingerbread. So the way we write the application is very modular, so it can run on Android as well as on PC. The main contribution here is that when you increase the number of phones, the average download rates increase. So in this scenario, we have 1, 2, 3, 4, 5, 6 phones, but only 4 phones have the 3G. So as you can see, so the overall rate of the group is the sum of the 4 phones, and then the next 2 phones doesn't have it. So we just flat out here. But the main things with the MicroCast allow is that the total bandwidth introduced into the local network is much reduced. So as you can see, if you don't use MicroCast, so this is the curve for BitTorrents, and you see when you increase the number of phones, the local traffic increases linearly. But in our case, it's just flat out like this. So it doesn't matter how many phones you have, we just send out the same amount of traffic. So here is one of the main results as well, so battery consumptions. So as you can see, this blue line right here means that the phone downloads the video by himself. So at the end, he has about 96% of battery, but it takes him a long time to download the video. So it's a 1,200 seconds. Now, if he collaborate, he can download the video a lot quicker, and then it consumes the same amount of battery. And then we also have some result on the coding rate when using network coding. So basically, we have both Java and C implementations. In the Java implementations, you can see we can achieve rate about, so this is the line. We can about 4 to 5 megabits per second in Java implementations. But when we go to the native C implementation, we get about 25 to 30 megabits per second when you use generation size at 25. So that's briefly what I work on.